Hello and welcome to this Java DSA tutorial. So in this video, we'll explore how you can do deletion in AVL tree. So deletion actually is complex than insertion because it involves multiple scenarios and in turn requires rebalancing also. In previous video where we discussed insertion, I've already discussed all these rebalancing scenarios where your tree can become left heavy or right heavy. So there are these scenarios, right? Left, left, right, right, left, right, right, left, where you need left rotation or right rotation. So all that I've already discussed. So that link I'll give in the description also. So that in this video we can discuss or focus only on these scenarios for deletion, because that itself is quite complex. You have many scenarios for deletion also. So in this video, I want to focus on that. So for these rebalancing things, you can see that video. Now coming to this deletion of a node in AVL tree. So deletion means you have to first find the node which you have to delete. So you have to search for the node. That is the first thing. Then you have to delete that node and you have to do rebalancing also. Whenever you delete any node, your AVL tree's height may again change, right? And it may become imbalanced. So you need to do the rebalancing also. So these are the steps. And coming to the scenarios for deletions, you have three cases within that also. If the node which you are deleting is a leaf node, that means it has no children. That is one scenario. Then the node which you are deleting has one child, either left or right. That is another scenario. And if the node you are deleting has both left and right children, that is the third scenario. So you have these three scenarios. So we'll start with this one. When you are deleting a leaf node. So this is the simplest scenario within the deletion, because if the node has no children, suppose you are deleting this node, right? It has no children. This is also null. This reference is also null. What you can do is you can just update the parent reference. This as null, correct? So whichever you are deleting, if we are deleting, suppose this node, then we can make this reference as null. That's all. Then it will be garbage collected. Or if we are deleting this one, then we can make this reference as null. So this is the simple thing you have to do. Left or right reference of the parent has to be set as null to delete the left or right child. And once you have deleted the node, remember to update heights and rebalance the tree to preserve the AVL property. So that is always there. So whenever you delete any node, you always have to update the heights and rebalance the tree. All right, so let's first write code for this scenario itself where we delete a leaf node. So we'll prepare the basic things for deletion, where you first have to locate also, right? Which node you have to delete for that value. You have to search the node, and then we'll code for this scenario first, where you have to delete a leaf node. So I'll do it within this one, which we have already done. So here we already have code for insert, which has all the scenarios also, LL, RR, LR, RL, along with right rotate and left rotate. So these things you'll need for deletion also. You have to again balance the node and get the height, all that you need. So we'll do within this. After insert, I'll start writing. So first thing is we have to do public void delete, and we'll get the value which we have to delete. Using that, I'll again call delete node, which will be called recursively. In this, I'll pass the root to start from there and the value, right? And I'll write another method which we can write private also. While making it public. So delete node. Here I'll get node root or node, whatever you want to call it, int value. So first check we can make if it is null. If node is null itself, we can return that node itself, which will be null only. So we'll return that null itself. Then we can do the scenarios. If value is less than node.left, that means you have to go on the left side. Otherwise, you have to go on the right side. If value is less than node.data, that means you have to go to the left side. Node.left equal to, again you'll call delete node with node.left and value. Else if value is greater than node.data, that means you have to go right. Node.right equal to delete node.right and value. Else you are at the node which has to be deleted. So let's print that also. Node to be deleted with value node.data. Here we have to make a check. So if we have to do for the leaf node scenario deletion, what can we check? That it should have node.left is null. At the same time, node.right is also null. So it is a node with both left and right as null. That means it is a leaf node. Let's write some message also so we can check. When we actually run it, leaf deletion scenario. Then we can do node equal to null. Okay, why that will work is because you will recursively call it, right? When you say node equal to null, you will return it. We'll write that part. So either you will come to this part from here or here, right? So you will send node.left equal to null or node.right equal to null. That is what you have to do, right? Node.right equal to null or node.left equal to null based on from where you are deleting it. So this will work here, node equal to null. And with that, what you have to do is you have to check all the height part also. So node.height equal to 1 plus math.max get height node.left left subtree or right subtree. In that you will add 1 and you will return what? You will have to call balance also. So return balance node and node. That is what you will return. Here also let's write if value is less than nodes data, that means traverse left, right? This is your value is greater than nodes data, that means traverse to the right. You are here, that means you've got the node. Here also we can write nothing needs to be deleted, means you don't have anything to delete. So this is our leaf scenario. If we run it, we were already running it, right? And I showed you that I already have one Java Swing graphic code which shows me graphic also for that. So this is our tree. So if I delete any of these, right, -1, 2, or 6 or 11, that should work. So let's say I delete this 11 first. For all this, I can write AVL tree dot delete 11, and let me do the same thing again. or actually it will refresh it that itself, which is already there. Keep it, and there is an error because node is null. Oh, sorry, I forgot one thing. That is why you have to do here itself. If node equal to null, then you return node itself. Then you don't need any height or balancing because that was the last one and it is deleted. So if tree has only single node, right? So once we go there, this is the node where we are and we delete it, then we don't need any balancing and all. We have to make this check also. Let's run again. So if you see 11 is deleted, right? Both are refreshed. So initially it was like this one, right? Then 11 was deleted. Right now only this leaf node scenario will work. So if I delete 6, that should also work. Again, let's see. 6 delete, so 6 is gone. In this case you don't have to make any other change, so it is okay because you just have to delete the leaf node. Then we come to the second scenario where we have to delete a node which has one child. So here it was leaf node, now scenario where node has one child. So if you are trying to delete a node which has only one child, then you have two scenarios, right? If deleted node is the left child of its parent, then if deleted node has a child, whether it is left or right doesn't matter, it will take the place of the deleted node. So if deleted node is the left child, that right or left child of this deleted node will become the left child of the parent. And if deleted node is the right child, then its child, whether it is left or right, that will become the right child of its parent, right? So that is what will happen. So here we have that case, you can see here. So this is parent node to be deleted is this 35. It has one child. What will happen? This is right child, right, which is deleted, this one. So this child of this deleted node will take the place of the deleted node itself. So that will become the right child of the parent. This is your parent. Okay, so deleted node is the right child of the parent. It has a left child, but it becomes the right child of the parent. So simple way to remember it, whatever you delete, that is replaced by its only single child, right? It has a single child, whether left or right, that will replace that deleted node. So this is your single child scenario. So if we have to code it in else part, after this we can take this scenario. Deleted node has a single child scenario. Node dot left equal to null. If it is not going there, that means both are not null. Then we check if node dot left equal to null. That is having a right child, right? So what you will do in this case is node equal to node dot right. Okay, then we'll have the left child scenario if it has only one child, and that is left child. That means node dot right equal to null, right? This also we'll see. And here we will have the having a left child. That means node dot right is null, double equal. Then what you will do is node equal to node dot left. Why that works is here, right? So this is the node you are deleting. So this is node. What you are saying is node equal to node dot left. So it comes here, right? Node dot left, whatever is that, that becomes the node. And this is what you will return. Again, it is recursive, so you have to think like that. Node dot left or node dot right, you will return to node dot left or node dot right. When this is called with node dot left, means you will connect with this node dot left or node dot right. So that is the single child scenario. So if else if. Then we have the last scenario where the node which has to be deleted has two children. Now let's check how this single child scenario actually looks like if we delete a node which has single child. Okay, so for that again I have to, let's first comment it. We see the tree. So this is our tree. Now if we have to do for single child, we have this 0 or 10, right? So let's try to delete this 0 first. What should happen is it has a left child. This is also a left child. So this should come here, right? -1 should come here. That node should take place of this node, right? So if we delete 0, so this takes place of this, right? Otherwise it is okay. Now if we delete this 10, it has a right child, 10. When we delete 10, it actually, if you see, causes a rotation also, because it was 9 was here, right? Now it is here. That means we had a right rotation, LL scenario. Here we see, right rotate around 9. Because if we delete 10, what will happen? Against okay, so if we delete 10, it will become left heavy, right? That is why we will have a right rotation. One will come here, and any right child of this node will become the left child of root node. That is why this whole thing will come on this side. That is what has happened, right? Yes. So that is why we always have to do balancing also whenever we delete any node. So this was the scenario for deleting a node which has a single child. So this case 3, deleting a node with two children in AVL tree. So when it has both children, right, the node which is deleted has two children. In that case, what happens? You have to find the in order successor of the node which is deleted. So in order successor is the next node which has the value greater than this node which is deleted. So you have to find the next highest node than the node which is deleted. So for that, what you do is you have to start from the right child of the node to be deleted. Node dot right, you will do first thing. Then you will traverse down the left subtree, starting from this right child, until you reach the leftmost node. So node dot left has to become null. You have to go till there. From node dot right, you have to start traversing node dot left unless until you come to the point where node dot left is null. That node becomes the in order successor, right? Now within in order successor also there are two scenarios. So if in order successor is the right child of the node to be deleted, that means you come to the this point, start from the right child of the node to be deleted, and it doesn't have any left subtree, right? No left subtree exists. Then this is the in order successor. Second scenario is you have a left subtree and you have to traverse that and find the leftmost node. So these are the two scenarios. Now based on that also you have some different implementation. So suppose It has only right child. After that, nothing else. So in that case, what happens is you have to update the parent of the deleted node to reference the in order successor, and a left child of the deleted node as the left child of the successor. Let's try to understand with this. So this is parent. So this is the node which you want to delete, suppose, right? What you will do is you will go to the right child. There is no left subtree. So this itself is in order successor, correct? Now what you will do is parent of the deleted node will start referencing this 50. This will start referencing 35. And if there is any left child, that will be assigned as the left child of the successor. So it will go here and this will become its left child. That's what you'll get. Now suppose it has a left subtree and you have to go through that to find the in order successor. Then what do you do? So successor's right child becomes the left child of its parent. And parent of the deleted node will start referencing the successor node. And any right and left children of the node to be deleted should become the right and left children of the successor. Again, easy to understand from this. Suppose this is the node to be deleted, 30. So you will start from the right, then you will go here, left subtree is there, then you keep going left, there is nothing. That means this is the in order successor, right? What you have to do is in order successor will take the place of the node which has to be deleted. That is one thing. So they'll go here, 32. And whatever was the left and right child of this parent, that will be referenced by this in order successor. This is okay, right? Parent of the node to be deleted should start referencing in order successor, and right and left children of the node to be deleted should become the right and left children of the successor. Correct? One more thing is successor's right child becomes the left child of its parent. So if successor has any right child, there is no left child. That is why this is the successor, right? But it may have a right child. That will become the left child of its parent, successor's parent. So this 33 will go on this side, right? So that is what you will do if there is a left subtree. And whenever you do a deletion, don't forget, always you have to do this height and rebalancing of the tree. Okay, so if we have to write code for the scenario, if the deleted node has both child, that means here if we see, we will be in the scenario of else. Leaf node, one child, if we are coming here, that means node has two children scenario, right? Node to be deleted has two children. I missed, right? As right child. Left. Now here if you come, that means you have to find a successor. We have to write a method find successor for this node. Node find successor. So we don't want to mess with this node because we have to, this is the node to be deleted. So we'll use a new one, node current equal to node. Then we can check if current dot left, we have to go right. It is null. We have come to that part. Then we can return current. Else return else what we can return, all this itself with current dot left, right? That will be finding the successor. That is what is returned here. That means here we can take it as node successor equal to this find successor. This is find the in order. Now once we have the in order successor, then what you can do is, so there is a trick actually which is done here. What you do is you replace the value of this node with the successor. Node dot data equal to successor dot data, because anyway successor replaces the node which has to be deleted, right? Whether it is this case or this case, right? 35 goes here, 32 goes here. So what we'll do is we'll do like this. We'll copy that data there itself. Then you can delete the successor itself. Call it with successor.data. And that you will give to node.write. So what you'll do is you'll call delete node with node.write and successor data. Let's try to understand here. So this you'll copy here. That is one thing you have done. This data you've copied here. So this becomes 35. Now what you do is you are saying delete the node which is on the right side of this node. So node.write and value 35. So you'll start from here. This is single child, right? Single child scenario, it will become right. So it will replace this with here. 37 will come here. Or in this case, if you see, you'll copy in order to here. And then what you'll do, you'll call delete from here, right? Node.write. So it will again locate this node that it has to delete this node. So your deletion will run from here. Recursive, right? So it will come to this part from 35 to 32. Then it has the node which has to be deleted. Again, single child. So this will come here because you're calling delete node, node.write. It will again call delete node, right? And in both of the cases, it is going to the single child scenario. That is how you do a two children scenario. Okay, so this is our two children scenario when the node which has to be deleted has two children, where you have to find the successor, right? Start from the right child of the node to be deleted. Okay, mistake here. You have to start from the right child, right? So successor we start finding from node.write, not from the node itself. Then we have this as already explained, right? So it's a small trick. You just copy it and then you delete the node from the right side. You start. So you'll call the same method from the node.write. So let's try to do this one also. So again, let's first keep it commented only and first see. So we have this node which has two children, then this node, right, which has two children. So let's first delete this 5 and check. In this case, it will go to this and stop here itself. It doesn't have any left child. So this will replace it. When we delete 1, then it has this. This will be the next, I mean, in order successor of 1. So this will take place of 1. 2 will come here. Let's first do with 5. AVL tree delete 5. So 6 goes there, right? That's the only change. Now let's do with 1. So again, this is our AVL tree. Now what we are going to do is we are going to delete 1. So 2 should take the place of 1, right? Because this is the in order successor. You go right and then find the leftmost. So this is the leftmost. So this will take the place of 2. That is what should happen. So 2 is coming there, right? In place of 1. So successor's right child becomes the left child of its parent. Successor had no child, so this is not needed. Right and left children of the node to be deleted should become the right and left children of the successor. Right? So this is happening. So anyway, it is replacing it. So the left and right child of the node to be deleted becomes the left and right child of the successor. Parent of the node to be deleted should start referencing in order successor of the node to be deleted. Parent of the node to be deleted was this, right? That starts referencing the successor. So these two are happening. So this is your scenario when node has 2 children. All right, so this is about deletion, where we have these scenarios, right? This is leaf deletion scenario. This is when it has single child, right child, left child, and this is 2 child scenario. This is the new method which has been added for that. Now, if we have to see the time and space complexity of this AVL tree deletion, so when we delete any node, right, we have to locate it. That is like when you insert or search, you go left or right. So go the whole depth, which is log n. So this is O log n, right? So this is for locating the node which has to be deleted. Now, when you delete it, then if it has 0 or 1 child, it is a simple replacement O1. But if it has 2 children, then again you have to find the in order successor, which may take O log n time in worst case. And you also do rebalancing, which may also take O log n time. So if you see time total, it is this. But you don't take the constant, so you won't take 3 log n. It will be O log n only. And space complexity, if you are doing by recursion, then you are going through the whole depth of the tree and you will have to add that many times in the recursive method calls, right? So your space complexity will be O log n. But if you use iterative method, then you don't need recursion step, then it will be O1 space. So that is the time and space complexity of the AVL tree deletion operation. And that is all about the AVL tree deletion. Thanks for watching the video. Please don't forget to like and subscribe.